Okay, everybody, good afternoon. We will have one seminar this week by Martin Licht from San Diego. I should also maybe mention that next week there will be no seminars in this series because of the workshop. So this is the only one. So please, Martin, you will talk about newest result in newest Vertex Bisection, please.
Yeah, thank you very much for the opportunity to give a talk here. It's a pleasure to take part in this program. So I will talk about some recent research together with Michael Holst and Zhao Lyu. This research, in fact, developed from an undergraduate research project that Zhao Lyu took part in while she was in San Diego. And what I will talk about is generally the topic of mesh refinement, and within mesh refinement we have this algorithm called Vertex Bisection, for which I will present some recent results. So first I will give an outline of mesh refinement in general, and in particular its relevance for numerical simulations. This will also include an outline of finite element methods, because I think we have quite a crowd here with different backgrounds, so I would like to get us to the same page. Then, having outlined mesh refinement, I will give an outline of new vertex bisection. And the main result, in fact, will be the amortized complexity analysis of new vertex bisection. And finally, I give some future directions of research that might be interesting in the future. So, let's first start with some very simple model problem and some finite elements. So, let's say we have a two-dimensional Lipschitz domain. And on this Lipschitz domain, we consider the Poisson problem with directly boundary conditions. And of course, this Poisson problem actually should be written in, or can be written in a variation formulation, specifically the weak formulation. For example, if f is in L2, then we search a function u in the Sobolev space H1 with directly boundary conditions. We have the standard weak formulation, and of course, we know this weak formulation is also valid when f is maybe not a function but a distribution in the dual space of H10. And yeah, we do have the standard solution theory. This weak formulation of the Poisson problem has got a unique solution, and this unique solution specifies these natural norm estimates. And towards a numerical method, we would like to replicate this formulation in a manner that is more amenable to perform it on a computer. And well, finite methods in some sense are a special case of Galerkin methods. So let me just give you an outline of Galerkin methods. So the principal idea is we use the same formulation that we had before, but we perform it over a smaller subspace. So we pick our Galerkin subspace V, which is the subspace of H10, and then we have this weak formulation where now the variable of the solution is stored within this Galerkin subspace, and also these test functions here are now stored within the Galerkin subspace. What's nice about this is that we can replicate the solution theory. We can replicate the proofs for that and gets a existence, uniqueness, and stability results for this formulation. And what is very nice about Galerkin methods is that we have some standard methods to derive approximation estimates. For example, I would like to use this Galerkin solution of this variation problem here as an approximation to the solution of my original problem. And the question is, how good is that as an approximation? Well, the standard result is known as GCS lemma and gives us quasi-optimality of the Galerkin approximation. Namely, the difference between the true solution and my Galerkin solution is up to some constant the same as the best approximation of my true solution from the Galerkin space. Okay, so the nice property of Galerkin methods, and I would like to, what is a concrete Galerkin method? Well, finite element methods are a special case of Galerkin methods. And there's a special choice of the subspace V. Namely, suppose that omega is a polyhedral domain and that T is a triangulation of that domain. And let's say we pick some polynomial degree R, then SH, which is supposed to be by Galerkin subspace, is now defined as also functions in H10 that on every triangle are polynomial of degree R. Okay, that's a standard definition of the Galerkin subspace of the finite element space, and then I can impose this finite element problem, finding a solution in the finite element space of this weak formulation that is only tested with the finite element functions. And yeah, I do have this quasi-optimality result of the Galerkin approximation. And now the question is, how good is the approximation? Since I'm working here with piecewise polynomials, I can utilize standard approximation theory for polynomial approximation. And what I get in the end is that the best approximation error in the finite element space is bounded by the HS norm of U for some suitable S and some power of H, where H is the maximum triangle diameter. Which basically means that the more regularity I have, the higher I can choose the polynomial degree, and I get a better approximation estimate. What you can tell here is that if I've got a triangulation and let's say, or maybe a sequence of triangulations where the diameter goes to 0, then the approximation, this error estimate will get smaller and smaller. So that's already one reason why we care about mesh refinement. We would like to cut, given a mesh, we would like to take the triangles and cut them into smaller triangles over and over again in order to get a finite element space with sufficient approximation power. This all translates into a linear system of equations on a computer. So we have this finite element space, and if you choose the basis for the finite element space, then this translates into a linear algebra problem. The weak formulation can be written as a linear system of equations. For example, if R is equal 1, if P has linear elements, then a common choice of basis are these so-called head functions that are everywhere 0, except P's has linear functions that are 0 at almost all vertices except at one single vertex. Well, these basis functions that we use in finite element methods typically are localized, which means that the matrix that results is sparse. And what also matters in practice is that the condition number of the matrix that we are dealing with depends on the mesh size. So for example, as the mesh size gets smaller and smaller, the condition number of the matrices deteriorates. And they also depend on the shape of the triangles. For example, in triangulation, we would like to have triangles that retain a nice shape. If we have very flat triangles, for example, then the condition number of the matrix will again get worse. Okay, so what is the role of triangulations in finite element methods? On the one hand, we need some description of the domain. If we want to solve a partial differential equations on a computer over some domain, then we better have a description of the domain on a computer. And triangulations are one way to do that. And second to that, triangulations also used to describe the Galerkin subspace, the finite element space. So we have these two purposes of a triangulation. And the second purpose is the reason why we actually are interested in manipulating triangulations. Given a triangulation, we would like to have a computer program that manipulates the triangulation to achieve certain approximation estimates. For example, we would like to have an algorithm that refines a mesh and cuts triangles into smaller triangles over and over again, in a manner that we can use the triangulation for to define finite element spaces. Okay, let's take a look at one example. Let's suppose we have such a domain here, like the so-called L-shaped domain, starting with 6 triangles. What I can do, for example, is that for each triangle, I take edge midpoints and connect the edge midpoints internally. That cuts each triangle into 4 smaller triangles. So, for example, let's take a look at the bottom right triangle. I cut it into 4 smaller triangles, and keep repeating that each time. And I get a very fine mesh in this example. As you can tell, the number of triangles explodes every time I perform such a refinement. So like it gets quadrupled each time. So the number of triangles increases exponentially. And some similar statement is true for the vertices. In particular, since the number of vertices corresponds to my the size of my linear system of equations in the end. So what you can tell is that if I keep refining a mesh in that manner, then the dimension of the linear system of equations increases exponentially.
Exponentially. Well,
each step gets multiplied by 4. That's exponential, is it?
No.
I would say so.
Yes.
Oh, yeah, in the number of refinement steps, you mean?
Yeah.
Oh, yeah, okay. I was thinking in terms of age.
Okay, that's it. So the dimension of the linear system of equations increases exponentially. It might happen, however, that actually you need this final resolution only at certain parts of the mesh. For example, if I know that my solution, that let's say the specific features of my solution are located in, for example, this oriented corner of the mesh, then I would like to have an algorithm that refines particularly in this corner and maybe not as much in the other parts of the mesh. Okay, such an algorithm could, for example, produce such a mesh here, where we have cut triangles, but we cut in particular the triangles towards the corner. This mesh actually has been generated by a new Vertex Bisection, which I'm going to talk about very soon. And what matters here is that the shape of the triangles does not deteriorate. So we see some counterexample actually what goes wrong if we don't focus on that condition. So let's talk about new Vertex Bisection, and in general, okay, what could go wrong if I do mesh refinement? So I've talked a few times about the quality of shapes in a triangulation. So in fact, this quality of shapes is an intuitive geometric notion, and there are different ways how to formalize it. So some authors take, for example, the radius of the circumscribed circle of a triangle versus the radius of the inscribed circle. What I would like to use is this quotient here. So the quality of a triangle is measured by the diameter to the square over the volume of the triangle. So that is what I define as a shape measure of the triangulation. And whatever shape measure is used, in some sense these shape measures are all equivalent for the purposes of assessing the quality of triangulations. Now, for example, a manner of refinement defined in the textbooks is so-called midpoint refinement. If I take a triangle, then I fix the midpoint, the barycentric midpoint of the triangle, and cut the triangle into 3 smaller pieces. As I keep repeating that, what you can tell here is that the triangles become very flat. And in particular, also the diameter of the triangle does not get smaller. So that can go wrong, that the shape of the triangles deteriorates. On the other hand, if I've got a triangulation, for the purposes of finite methods, I would like to have a triangulation that is conforming or consistent in the sense that whenever 2 triangles meet, they either meet at a common vertex or at a common edge, and otherwise the intersection is empty. So, for example, if I take these 4 triangles here and cut this bottom triangle, and then cut the other bottom triangle, then in these places here I've got inconsistencies of the triangulation. And for many finite element methods, it's actually much more convenient if you've got triangulations that avoid such inconsistencies. Okay, in fact, uniform refinement, which we've seen previously today, satisfies these two conditions. It's geometrically stable and also avoids inconsistencies. But by definition it's global, it's uniform over the entire mesh, which means it's inefficient as if we want to refine locally. Okay, so before we describe the localized refinement algorithm, let's take a step back and see how this refinement algorithm is actually used. So what you typically have in applications is that you start with an initial triangulation, and then some user picks some triangles to be refined, and your algorithm refines these triangles. Then the user picks new triangles to be refined. These are refined by the algorithm, and that cycle repeats over and over again. For example, the user might be a finite element code. So the finite element code that measures like, okay, in order to achieve a certain approximation quality, I need to refine triangles in this corner, for example, and then it tells the refinement algorithm to refine the triangles in that corner. And the constraints that need to be satisfied is geometric stability, so the shape of the triangles does not get worse, or quantitatively the shape measure does not deteriorate, and of course its consistencies, so the triangle boundaries match. And with this algorithm, the resources of concern are of course the time and space complexity, and I would like to point out if the user marks certain triangles for refinement, it doesn't mean that only those triangles get refined, but in order to achieve the consistency, it might be necessary to get further triangles refined. So that actually makes the design of that algorithm quite integrated. Okay, so the idea of newest vertex bisection is as follows. If I've got a triangle, then we bisect from the most recently created vertex to the opposite edge. That opposite edge is always the oldest edge of the triangle. And as you keep repeating that one can show that the shape of the triangles does not deteriorate. So we can show in fact that the descendants of any triangle T, if I keep performing newest vertex bisections, belong to at most 4 similarity classes, and quantitatively the shape measure of these the descendant triangles is only slightly worse than the original shape measure. The only bound that we get is actually the shape measure of the descendant triangles is only 4 times the shape measure of the original triangle. Now, for example, like if I've got a triangle like the first one here on the left, I cut it in two, and I get 2 new similarity classes. If I cut these 2 again, from the most recently created vertex to the opposite edge, then I get on the one hand the first similarity class and another 4th similarity class, and then basically I'm in a cycle. So the newest vertex bisection will only produce these 4 similarity classes. Now, this describes a method to cut a single triangle. What we have not discussed yet is the consistency. So if I perform newest vertex bisection on single triangles, I get geometrically stable descendants, but the mesh might be inconsistent. So we need some method to actually combine these bisections to get a consistent mesh. So in fact, in the literature on mesh refinement and bisection methods, this research topic has been active for since the 1980s, but it seems at some point that people fundamentally switched the manner they organize these bisections. So first they have what I call a non-recursive approach. What they do is they mark certain triangles for refinement, then they perform the bisection, and then you get a new mesh where now you have typically you have certain inconsistencies introduced. And what they do is additional closer bisections. So wherever you have an inconsistency, you perform an additional bisection in order to remove these inconsistencies. These new bisections now may introduce again further inconsistencies. And the non-recursive algorithms keep performing these closure steps over and over again until no further inconsistencies have been produced. okay, one issue with this approach, of course, is that typically you would like to have, you only have data structures for consistent meshes in your code. And with that approach, you have to temporarily deal with inconsistent meshes. So we would like to have a manner to organize these bisections such that these inconsistent meshes never appear, not even as temporary meshes. And I would say around 2000, people have actually shifted towards a different algorithm, which I call recursive. And that now describes that we need a bit further theory. So we call a triangle T compatibly bisectable or compatibly divisible if its refinement edge is a refinement edge of all other triangles adjacent to that edge. For example, in this triangulation here, these two triangles have the same refinement edge, and I can just perform bisection and get 4 new triangles. These triangles here all the time have also been compatibly bisectable because the refinement edge only belongs to one single triangle. This triangle here, however, is not compatibly bisectable because its refinement edge is not the refinement edge of the other triangle there, of its neighbor triangle. Now the idea is, if I want to refine my mesh and want certain marked triangles to be refined, then I do that by a sequence of compatible bisections. I might first refine the mesh in a very different area, but then eventually I work myself through towards the triangles that I actually want to have refined. And in order to describe this, I would like to introduce a notion called dependency graph. So we say if the refinement edge of some triangle T borders another triangle S, then we say that T depends on S. For example, this triangle here depends on that triangle. And in this case here, for example, these two triangles depend on each other. So this introduces a graph theoretical structure. Now, the result is that if the dependency graph of a triangulation has no cycles other than these mutual dependencies, then compatible bisection will not introduce any other cycles except these compatibly divisible pairs. So, for example, in the worst case, it might happen that maybe I've got a triangulation and some cyclic dependencies that runs through the entire mesh. If the initial triangulation does not have any such cyclic dependencies that run over more than 2 triangles, then after a sequence of compatible bisections, no such cyclic dependency will have appeared either. So that's an invariant property. And that means actually that this property that no cycle appears is invariant under compatible bisections. And now the idea is if I have some triangles that I want to refine, for example in this case here, in order to get this triangle refined, I first refine that triangle, and then I will have a new neighbor for this triangle that is compatibly bisectable with a neighbor. So the idea of the recursive approach is to define a sequence of compatible bisections that gets the originally marked triangles refined.
So which one do you refine first?
First one I'll refine this here. Then I draw a line from this vertex to that one to the midpoint of the refinement edge. And this will be the refinement edge of the new neighbor.
Do you also bisect the lower triangle?
Eventually after that. So
you do have a period of time when you have a non-consistent triangulation.
No, the non-consistent triangulation never appears.
When you bisect the top one but not the bottom one.
For example,
I see.
I have this setting here, and okay, I refine this triangle first. Now this is the newest vertex, here's a refinement edge, and now I can bisect it like that. So the recursive algorithm can in fact be written in terms of recursion. Namely, the recursive bisection algorithm on some triangle T does the following. So as long as T is not compatibly divisible, I pick a triangle S on which T depends, but not the other way around. And for that triangle, I perform, again, my recursive bisection approach. That is repeated as long as any such triangles. And eventually, T will be compatibly divisible or bisectable, and then I perform the bisection along all triangles sharing the refinement edge along T. No inconsistent temporary meshes will appear in that manner.
So you pick a triangle T that you want to bisect, and then you run this algorithm, and then you have a much finer mesh that has, possibly finer mesh, that has T bisected and is still compatible.
Yes.
And then you look at that mesh to find the next triangle you want to bisect.
Yes.
Got it.
So I have this dependency graph, and given some triangle, I go first along the dependency graph until the end, and then I perform a sequence of bisections until I've reached my original triangle.
Can you remind me? T is not compatible if it doesn't share an edge with. Sorry, can you remind me what is not compatible mean again?
Compatibly divisible in the sense that if I've got a triangle and well, a triangle is compatibly bisectable or compatibly divisible if its refinement edge is also the refinement edge of all neighbors sharing the same edge.
So it's okay. So then the dependency goes back and forth.
Yes.
So we draw it as a graph, it would be a two-way.
Yes.
Okay.
So these short cycles between mutually dependent triangles are good, but any longer cycles are bad. Unfortunately, if the initial triangulation has no such longer cycles, they're not going to appear.
What if one triangle has two edges you want to bisect, or three edges,
Oh,
and then and one of them is not compatible?
That does not appear in the algorithm.
Okay.
So, but I mean, you could artificially do that, like if you repeatedly mark the triangle. And in this case, we actually, in this setting here, we are in the complexity of the algorithm eventually depends on the depth of this recursion. So one issue is actually that even if my initial triangulation has no long dependency chains, after a sequence of compatible bisections, it might happen that suddenly we have that we build up a long dependency chain. So it might happen that one single bisection after some time might trigger like a chain reaction that requires much more work than the previous bisections. So in fact, this amount of work has been investigated previously. For example, the first publication that I'm aware of that did that was by Binev, Dahmen, and Devor. And what they have performed was a so-called amortized complexity analysis. They've shown that even though a single bisection, a single call to the recursive bisection algorithm might take an arbitrary amount of time, or quite a large amount of time, the cumulative work is bounded in terms of the number of triangles that you've marked. So the number of triangles created is bounded by some constant times the number of triangles marked. So you do not perform much more work than that you request. That's the summary of this statement. And okay, well, one question actually that arises when you read the paper is that on the one hand, this constant lambda apparently depends on the geometric properties of the mesh, such as the largest diameter, the minimum volume, but the algorithm itself is actually independent of any geometric properties. It does not see the geometry. So this seems to be a paradox that we have an estimate that involves geometric properties of the mesh, but at the same time, the algorithm that is measured, in some sense, is not completely independent of the geometry. Another issue is that much of the literature about mesh refinement is stated only for domains, but we would also like to have mesh refinement for example, manifolds, surfaces, for example. So, and it is at least in principle conceivable that some parts of the algorithm depend on the topology of the domain. also the topology of the triangulations. You would like to check that actually these algorithms also work on surfaces. More generally, actually, you like to also have an algorithm that works for surfaces that are not manifolds. For example, if you've got such a surface here that contains a split, then okay, we still would like to have an algorithm that works for such surfaces, and it's not completely obvious that the bisection method generalizes immediately to such meshes like that. That, in particular, that this recursion step in the algorithm is really finite. I mean, such triangulations, for example, appear if you've got flows in fractal media. So it's actually relevant to have a refinement algorithm for such meshes. And previously I mentioned that the complexity estimate of use vertex bisection that you find in the literature depends on geometric properties of the domain. So what eventually it boils down to is that you have to compare the largest diameter in the initial triangulation to the smallest volume in the initial triangulation. You take the quotient of these two quantities, and there are examples actually where these quantities deteriorate. For example, if I've got such an approximate triangulation of a disk, I keep generating a finer triangulation, much finer triangulation, and the shape measure actually of all these triangles is bounded by probably 4.445. But well, the estimates in the literature on the amortized complexity of used vertex bisection will get progressively worse for such a disk. And this seems to be like very paradoxical. It should not depend on the geometry. So, as for manifolds, I can report that actually the algorithm generalizes. So the major parts of the algorithm generalize. It's not too much of a problem. If you want to take care of the geometric quantities in the complexity estimate, you have to do some modifications. Similarly, for the singular manifolds that contain splits, there actually might happen that refinement edges may be shared by more than two triangles. The dependency graph is not necessarily a tree. The dependency chains are not necessarily chains. They might split up, might join again. So the combinatorics get more complicated. However, the algorithm itself generalizes. And again, you need to actually take care of the geometric quantities in the complexity estimate. And we can also report that the initial distribution of refinement edges can be generalized. But I would like to focus on the amortized complexity analysis here, because actually it's the part of the that is basically the topic that has been puzzling me most. Like, you have a combinatorial algorithm, but the analysis of that algorithm involves geometric terms, as far as what literature is concerned. Okay, so in order to perform an amortized complexity that does not involve these geometric quantities, I will do some preparations. So first, we have all triangles in the initial triangulation, I say, have generation 0 in the triangle. Whenever I have a triangle of generation G that I bisect, then I say the children have generation 1 higher. Very intuitively. And you have got a theorem that says that the diameter of any triangle, as I keep increasing the generation, the diameter gets halved every other bisection, every other generation, and every generation the volume decreases by 1/2. Now the first result is the following, namely, if I've got a sequence of triangles, the first combinatorial result is that if I've got a sequence of triangles where Ti depends on Ti plus 1 but not the other way around, then actually the distance between these triangles can be bounded. So the distance between the beginning of the dependency chain and any other, and for example the last entry in the dependency chain, is bounded by c times 2 to the minus g over 2, where g is the generation of the last triangle. The intuitive idea is if I've got the diameter, it decreases as the generation increases, the diameter decreases. So if I've got some triangle of a low generation, all the triangles that depend on that first triangle will have a higher generation. And as I keep as I walk this chain backwards, the triangles get smaller and smaller. So the cumulative distance that I can walk will be bounded. And in fact, it is bounded by a multiple of this term here. So basically, this says that this distance is bounded by a multiple of the diameter of tk.
Is that theorem true if all you know is that Ti shares an edge with Ti plus 1?
Yes.
You're not using the dependency direction, right?
If
Just
Ti
these things
depend-
share edges so you can walk along that path.
Yeah, Ti depends on Ti plus 1. So I have a sequence where the T naught has if a refinement edge at borders T1, T1 has a refinement edge at borders T2, and I keep walking on until I reach Tk.
But if instead of that hypothesis, you just said T1 has a common edge with, T0 has a common edge with T1, T1 has a common edge with T2, you'd get the same estimate, right? Or am I missing something?
Yep. In that case, you would need to use the generation of the triangles.
You did use it. Oh, I see, the generation only of Tk. That's the point. Okay, that's the
Yeah.
one I missed. Thank you.
So, in order to get a purely combinatorial estimate, we have modified the proof of the complexity estimate. And we have essentially we've added another layer of abstraction. So I define the set here. Given a triangle T and some generation index K, I take a look at all the triangles of generation K, for which I have this distance bound here. And I would like to have that this bound here is uniformly bounded, where delta is some parameter. So in fact, this existence of this parameter of this constant C sharp delta is actually intuitively clear if you think about it. So all these triangles S in the set have a radius that are contained within a radius comparable to this term here around T. This is what this inequality says. And since I fix the generation of these triangles S, I have a lower bound on their volume. All these triangles essentially are contained in a ball with a radius comparable to Z, and they satisfy minimum volume estimate. So there must be only so many triangles that can fit into such a ball. In fact, the ball has an area comparable to delta squared times 2 to the minus k, and the triangles S have a measure comparable to 2 to the minus k. So only something comparable to the number of triangles in this ball, which means the number of triangles in this set, is at most a quantity comparable to delta squared.
What's T1?
Oh, that's a typo. It should be T. Thank you. And in fact, by purely geometric terms, you can actually derive a bound for this constant. And actually, this bound depends on the maximum diameter to the square divided by the volume of the minimum volume of any triangle in the triangulation. In our applications, this delta will actually be bounded by the maximum diameter. So in the end, the quantity that appears is essentially bounded in terms of the maximum diameter to the square over the minimum volume of any triangle. That's something you can derive immediately if you're working on a domain, but actually in the final part of the proof, we are going to use that theorem directly in a slightly different manner.
Are you assuming the initial triangulation, everything has generation 0 by definition?
Yes.
And the refinement edges can be arbitrary?
Arbitrary unless you have any cycles.
What about cycles?
Like unless you have this long dependency cycles. If you've got cyclic dependencies, then the recursion wouldn't stop.
So you're assuming you don't have cycles in the initial mesh?
Yes.
Is that always easy to achieve?
For example, you can, a greedy algorithm can do that. So it's easy to get actually a triangulation where the length of any chain is either one of these short cycles between neighboring triangles, or a dependency on one triangle that is already matched. So there's not an essential difficulty. Now, to get the main proof of this estimate of this constant lambda that appeared in the complexity estimate, the idea is as follows. I start with initial triangulation and T0, and let T be a triangulation that is generated after calling recursive bisection several times with some marked triangles. And the set of marked triangles M here is the cumulative set of all triangles that have ever been marked. So I keep calling this recursive bisection algorithm with marked triangles, and M in this case is the cumulative set of all the triangles that have ever been marked. And then I define this function lambda here. The intuitive idea is that every marked triangle, T prime, pays a certain amount of money to any newly created triangle T. And in fact, there are two constraints, namely every triangle T prime that is marked pays only a certain amount C to the dollar on the newly created triangles. And on the other hand, any newly created triangle gets from all the marked triangles gets a minimum amount C index dollar. Now, if you have such a function that gives such an assignment of sort of money transfers between marked and newly created triangles, then you can bounce a constant lambda by this quotient there. Namely, okay, the number of on the one hand, the number of newly created triangles times this constant here can be bounded by this term here. That's simply by expanding this, by summing over all the newly created triangles and using this upper bound on C index dollar. Then by rearranging the sum, you can change it into a sum of all the marked triangles, where you are where you're only summing up these upper bounds here, which gives you this term here, the number of marked triangles times this constant. Then then you immediately see that the constant lambda is bounded by this quantity. Okay, we need to define such a function, and that involves a bunch of parameters. Let me give a brief outline. So we have two sequences of real numbers. The sequence A, the sequence A starts at -1, goes to infinity, it's summable. The sequence B starts at 0. The first entry in the sequence is at least 1. And it's summable in a weaker sense. It has this weighted summability property. And the infimum of all the products between corresponding sequence members is bounded from below by a positive number. Then the function lambda is defined as follows, namely essentially how much money the marked triangle T prime transfers to the triangle T depends on the generational gap between the marked triangle and the newly created triangle. And the triangle T prime pays money to a triangle T only if the triangle T is not much younger than T prime, which is expressed in this inequality here, and if I have got this distance estimate. Delta here is some quantity that emerges from the proof.
Only 1 minute left, really, but
Oh,
yeah, but you can go a few.
that's what 5-2. Okay. Okay. You can actually find sequences AK and BK that satisfy the properties. And then, okay, for example, pick some marked triangle T prime. You sum up all the triangles T, and well, after some manipulations, you fairly easily get this upper estimate. At some point, you need to bound the number of triangles of a certain generation within a certain distance of marked triangle T prime, and that's where this term, this constant C# delta appears. Then you get this estimate. Next, we prove the lower estimate, but actually we don't because it's really complicated. And after all these complications, what you get is this estimate here. Lambda is bounded by this term, where we have some numerical terms and this constant C# delta, which still depends on the mesh. So if you plug everything together, all the estimates that we have, eventually you get this quotient here. The constant lambda is bounded by this quotient, the maximum diameter to the square over the minimum volume times some numerical constant. And I would like to remark, you never see this estimate fully spelled out in the literature. So I'm not saying that this numerical constant is optimal, but on the other hand, there's no, there doesn't seem to be a better result fully spelled out in the literature. However, we're still concerned about measures like that. So we would like to have a purely combinatorial estimate that does not depend on the geometric quantities and gives us reasonable results with such meshes that are highly non-uniform. So in fact, to achieve that, we use a trick from topology. So we have our triangulation T, and okay, our first thing, I number the vertices of the triangulation, V1 up to Vn. And what I do is I construct reference triangulation in a high-dimensional space. So for every vertex Vi corresponds to a unit vector Ui in the space R to the n, where n is just the number of vertices. Every vertex now becomes a unit vector in some high-dimensional space. Then whenever I've got a triangle in the initial triangulation, Vi, Vj, Vk, then I put in a corresponding triangle in this high-dimensional space, and I choose the refinement edges of this reference triangulation also accordingly. So I really just take my triangulation and transform it to a reference triangulation in a high-dimensional space. And as you can tell, all the triangles are essentially looking the same. So the geometry of the setting is completely standardized.
So how do you construct UI from BI? How do you?
I just say, okay.
You just take the values of the.
Yeah. UI is just a standard unit vector in direction I.
So all these unit vectors are mutually orthogonal.
Yeah. The standard unit basis vector. The standard vector basis for R to the n. So if I perform New's vertex bisection over my original triangulation T, that corresponds to New's vertex bisection over this reference triangulation. The geometric quantities, however, are now completely standardized. So that gives us a chance to actually achieve a geometry-independent complexity estimate. So what I get is this estimate, where I now have a new constant, namely Cn is the maximum number of neighbors of each triangle. So I need an upper bound on the adjacency of the triangles in the triangulation. So in order to get this estimate, where now all geometric quantities are standardized, I need an upper bound. I take this estimate that I derived previously, but now make a different estimate of C# delta. Namely, I estimate it in terms of Cn. And then you get this lower bound there, this upper bound there. Lambda is bounded by some numerical constant times something that only depends on the adjacency constant.
So essentially, you put in the vertices on the unit of on the simplex in dimension capital N.
Yes.
Is that right? You're
Yes.
putting the so you're triangulating the simplex.
Yes. So every vertex now corresponds to a standard unit vector.
Well, he's not triangulating the simplex, he's still making a two-dimensional triangulation whose vertices belong to this billion-dimensional simplex.
Exactly.
Because n, what is n again?
The number of vertices.
All right.
So if I've got a billion vertices, I really have got a billion dimensional vector space.
Like it's going to be like a subcomplex of the two skeleton of the standard n simplex.
Yes.
This is complex.
It's sort of like you leave the topology of the triangulation alone, but you turn every triangle into an equilateral triangle of the same size, and you use as many dimensions as you need to be
Yes.
able to fit that structure.
Yes. That's in topology. It's known as I think the standard embedding of a topological complex. Okay, so that gives us the completely combinatorial estimate and future directions. The amortized analysis is actually a technique from theoretical computer science. So there are different methods in theoretical computer science known how to perform such amortized analysis. And the question is, okay, can we actually improve this amortized analysis? Then you would like to do this for high dimensional spaces too, for example, three-dimensional space, three-dimensional triangulations, and in fact it works. So the most of the proofs techniques generalize, and completely different from that is parallelism of bisection. I think uniform refinement is very easy to parallelize, but it's not clear to me how you can parallelize actually these localized bisection methods. So thank you very much, and I welcome your questions.
Questions?
It seems like, so I guess I have a couple of questions. One is, so it looks like the way your proof works is you do something using the geometry, and then you have a trick to make the geometry uniform, and then you apply it to that uniform geometry. But the algorithm is completely combinatorial, so how does geometry come in the first place? How do you use geometry in the proof?
So much of these proofs are, or the proofs that I've used here are found in the literature in that manner. So they have slight variations what you find in the literature. So what we've done is we have taken these proofs from the literature and worked out, okay, what are the quantities that actually appear there? And then we worked out how to standardize these quantities, how to avoid these geometric influences.
The other question I was going to ask is this feels a lot like some sort of algorithm on a directed graph. Is there any way of applying results from graph theory to this problem?
That's a very general question, and I know one part actually, namely the choice of initial triangulation. So Doug asked how to find the initial triangulation. How difficult is that? In fact, there's an algorithm for triangulations of domains that finds you an assignment of refinement edges such that every triangle is matched with some other. So basically, it's a perfect matching algorithm that they use. So there are some applications of graph theoretical methods that actually can be used for such estimate for this problem setting.
All right. So no further questions. Let's thank the speaker once again.